and next week what will happen is again uncertain. So it's necessary to change our plan so that at least the basic material which we have essentially have to cover is covered within the semester. So then our thermodynamics part will have to wind up at this point. Now, so far we have done mostly fundamentals. We had started with application, what are component efficiencies. Now, the next logical step would be to actually consider various cycles, engines as well as refrigerators, and see what is the difference compared to a Carnot cycle. The Carnot cycle is the ideal. The Carnot cycle gives you the best performance, but operational difficulties why we cannot design an actual engine or a refrigerator to follow the Carnot cycle or the reversed Carnot cycle. So the actual cycles are slightly different. There are reasons why it is different. Those are explained in books. And if they are different, their efficiencies are also different. So how do you calculate the efficiencies? So this is application of the fundamentals to actual cycles. I wanted to cover it because that shows you the relevance of what we have covered so far. But seeing the way things are going, I think it's necessary to stop the discussion on that. But this is the right time when, if you read it up, you would be able to understand how to analyze an actual cycle. So what I'll do, I'll leave this as an exercise to you to read up on your own. So the chapter in Van Wylen and Sontag which you have to read up would be this chapter has a large number of sections. So I'll just mention which are the essential ones which you have to read. The Rankine cycle, which is used in steam power plants. It's also used in nuclear power plants. The Brayton cycle, which is used in gas turbines, and these are used in aircraft. They are used in for power generation also, but more widely used for aircrafts. Then there is the Otto cycle, which is used in petrol engines. So these are used for converting thermal energy into work. So that work may be in the form of electricity or it may be in the form of shaft power. And then the reverse cycle So these are the essential cycles which you need to study. So then I'll leave this as an assignment to you. Read up this. Then we can discuss for the next class test what should be the syllabus. So if you're ready to study this on your own, then we can include this as in the syllabus for the next class test. In which case, probably the next class test, it was normally scheduled to be held in the first week of October. I might hold it after the break. You get a break during the Shera Durga Puja time. So I can give you that extra time to prepare and then hold it after the break. So just have a look at this material in the book, and we'll discuss whether to include or not include this in the next class test. Now,
Sir,
yes,
these are all present in Wozniak Sontag book, sir.
yes, these are all there.
Okay,
In
sir.
fact, these are very basic material. So apart from Wozniak, any other book on basic thermodynamics would also discuss this. So another point which you have been making, the students have been making, is that the amount of screen time is very high, which I understand is putting eye strain. Now, since you're at home, you don't have access to the library, so library books are not available to you. One of the options is if you can buy the book. Now, I don't know whether you'll be ready to buy the book considering that you are manufacturing students. So for manufacturing students, probably you would not want to buy a book on thermal engineering. One more option which is there is, instead of seeing everything on screen, that way you're spending a lot, almost the entire day looking at the computer screen. The other option is PDF files of these books are available. So if you have to study one particular chapter, you can probably print out that particular chapter. So if you have a printer, you can do that. The cost comes out okay if you use refilled cartridges. Alternatively, many of the photocopying centers now accept a PDF files on a pen drive. So they are ready to give you a printout of whatever pages you want. So if that is available at the cost of photocopying, then printing out a few chapters from a book may not be very prohibitively costly. So these are options which you could try out, because then you don't spend all your day looking at the computer screen. So now let's come to textbooks for the fluid mechanics part. Let's switch over now to the fluid mechanics part. These are the commonly used books for the first course on fluid mechanics. These have all been used sometime or the other as the textbook for the first course on fluid mechanics. Now, unlike thermodynamics, where we were dealing with um, the entire material inside a device being in thermal equilibrium. So we treat, so at least when we say if we if we consider a certain device, say a boiler, we assume that in various parts of the boiler, the material is at certain temperature, certain pressure, which does not change with time. So the balance is essentially between what is flowing in, what is flowing out. So then we assume that the properties at the inlet and at the exit are uniform. So we do not bother about spatial variation at the inlet or at the exit, and that is what determines the balance. So spatial variations were really not something we bothered about while we studied thermodynamics. Unlike that, in the case of a fluid, when water is flowing through a pipe, we sometimes bother how does the velocity uh, vary as a function of our position inside the cross section of the tube. So if we are closer to the wall, if we are closer to the center, how does the velocity change? So therefore, we should have some governing equations for a fluid. So deriving the governing equations will be the first step. Once we derive that, then we'll solve it for a few simple configurations, and then we'll go over to some other specific applications. Now, if we are to derive the equations governing the dynamics of a fluid, the starting point, it seems, would be that for a point mass. So Newton's laws apply to a point mass. So if I have a particle, its motion is described by position and velocity of the particle. So then, if you know the position and if you know the forces acting on it, the forces acting on it may be a function of position. In that case, if you know the position, you know the force acting on it. If you know the force acting on it, you know what is the acceleration. So Newton's law tells you that. Then, um, if you know the force acting on it, then Since it's a second order ordinary differential equation, if you know the initial value of position and the initial value of velocity to initial conditions, you can integrate forward and calculate what is the position and velocity of the particle at future instants of time. So the motion of the particle is specified by the position and the velocity of the particle. Now, if you have a system of particles, then so if you have a number of particles, then if you specify the position and velocity of each of the particles at a certain instant, and let us say we know these may be interacting with each other. So if they are charged particles, they have a electrostatic force acting between each other. So then that force law tells us what is the force depending on what the positions are. So if you know the positions of two particles, you know what is the force acting between them. So if you know the initial position and velocity, from that you can calculate what is the force acting on each particle, and each particle is governed by Newton's laws. So if you know its initial position and velocity and you know the force, you can integrate forward. Now, since the force acting on this particle depends on the position of this particle as well as this, so it's a coupled system. So it's a system of coupled ordinary differential equations. But um, even if you cannot get an analytical solution, you can always integrate it numerically and calculate the position and velocity at all future instants of time. So the system of particles, its motion is described by the position and velocity of each of the particles. If you have a rigid body, its so here, although you have a large number of particles, since the relative positions are do not change, it's a rigid body. So a few gross coordinates specify the position and the rate of change of position of the rigid body. Now, for a fluid, let us say we have a tank of fluid. Water is coming in through an inlet pipe, and it flows into the tank, which has water up to a certain height, and it flows out through an outlet. So let's suppose this height remains constant. So then if I use a long tube and inject a small drop of dye in the fluid, I'll see it gradually moving this way and finally going out. So if I follow that dye, it will be moving with a certain velocity. So if I assume that the blob of dye is going with the flow, whatever the velocity of that blob of dye, that is the velocity of flow at that position. So then as it moves along at various instants of time, I can find out what its velocity is. Now, since a fluid, the relative position of different elements of the fluid. So if I consider it to consider a small element of fluid anywhere inside the fluid mass. So the relative position of different elements is that does not remain fixed. So therefore, the velocity can have any value independent of its at any position. It can have any value independent of what value it has at other places. So just as for a system of particles, we had to specify the velocity of each of the particles, here we have to specify the velocity at every position. Now, in our basic fluid mechanics course, for that matter, when we are considering the material as a fluid, we are ignoring that at a microscopic level it's discrete. At a microscopic level it consists of molecules which move around at random. But then we assume in fluid mechanics that all variations, say the length scale over which velocity changes significantly, those are over a length scale which is significantly larger than molecular scales. So then on that length scale, it can be considered to be a continuous material. If it's a continuous material, that means I have the properties like density, pressure, velocity. Those have values which vary from point to point. So then at any point, at any given instant of time, if I have a tagged particle in the fluid and I follow its motion, so at that position, at that instant of time, whatever its velocity, that is the velocity at that point at that instant of time. So if I use Cartesian coordinates, then the x component of the velocity of that tagged particle is this. Similarly, I'll have a y component, and which varies with position and time. Now, to get the velocity, we usually use um, some material whose movement we can follow and which moves with the flow. So various options are, say if it's a liquid, you can inject a drop of dye. If it's gas, you want to study the movement of air, you can inject a small amount of smoke. So then, how does that blob of dye or the small amount of smoke move with time, and how is it related to the velocity? So for that, there are certain terminology used. So a streamline is a line which is everywhere tangent to the velocity vector. So at any position, the streamline is a line whose tangent is in the direction of the velocity vector. That means um, if you if you go in any direction normal to the streamline, there will be no component of velocity in that direction. So there is no velocity. The velocity is always tangent to the streamline. So there is no component of velocity perpendicular to the streamline. So therefore, if you have a streamline, there is no flow across it. So if you can, um, uh, so at any point, if this is the velocity, the streamline there passing through that point is in the direction, has the tangent along the velocity. So then, if I take a certain ring and draw the streamlines through every point on that ring, then I get a stream tube. So if I have a stream tube, so this could be a stream tube. So if I have a stream tube, again, every line on the stream tube, so this stream tube consists of a set of an infinite set of streamlines. Now you never have a velocity normal to the stream to a streamline. So therefore, you cannot have any velocity normal to the stream tube. So therefore, whatever the velocity enclosed by the stream tube, remains unchanged. Whatever the fluid enclosed by the stream tube remains unchanged, because no fluid can move across the stream tube. So path line is the actual path traversed by a given fluid particle. So how do you plot a path line? So in this case, the setup which we were considering earlier, you have a fluid flowing in from here, and you want to find out what is the velocity distribution in this. So with that purpose, you inject just one drop of fluid at some time inside this flow region. So then that drop of dye will move with the fluid, so it will trace out some path in this manner. Now, if you take a photograph using a time exposure from the time, so you keep the shutter open from the time you injected the dye up to the time when it finally left the tank, then you'll get the path line of the drop of dye in the tank. So that time exposure will give you the path line. So the difference from a path line and a streak line is that for a path line, we inject one drop of dye and take a time exposure and follow its path. Now for a streak line, what we do, we keep on injecting dye, and at a later instant, we take an instantaneous photograph. So then the line which we'll get were the set of points, all of which pass through this point at an earlier instant of time. So if I start at time t equal to 0, and let's say the dye which I injected at t equal to 0 leaves at time t equal to 10, then at t equal to 10, if I take an instantaneous snapshot, the particle which was injected here at t equal to 0 will be here. The particle which was injected at t equal to 1 will be somewhere here. At t equal to 2, that will be somewhere here. So this is the a set of points, set of particles which earlier were at this point at some earlier instant of time. So for a path line, we inject only one particle and take a time exposure of its path, whereas for a streak line, we keep on injecting particles and at a later instant, take the instantaneous shot of all those particles which have been injected over that time. Now, this is a favorite topic for gate questions. Now, since you are from manufacturing, I presume if you intend to appear for gate, the questions you'll face would be more on manufacturing. So I think the gate question aspect can be ignored, and reassuringly, so if you have, so say at one point you have an incense stick and you're releasing smoke, and you see how it because of air currents, what is the path followed by the smoke. Now at certain instant of time, if the wind direction changes, then the direction in which the smoke will go will also change. So then path lines and streak lines will become different. Now, if it is a steady flow, then there is no difference between a path line and a streak line and a streamline, and they are all the same. So if you want to solve a set of solve problems, there are problems on this in books. So those problems bring out what are the situations where path lines, streak lines, etc. could be different, but that seems to take us away from the direction in which we wish to go. So I'll not go into further details of that. Now, how do you describe the physical variables in a fluid? Now, what are the physical variables of interest? So we are trying to study the dynamics. Now, in the dynamics of a particle, what are the quantities we need to know? We need to know what is the velocity of the particle. How it will change will depend on the force. So for a particle, we need to know what is velocity. How the velocity will change will be governed by force, and not only is it governed by force, it is also governed by mass. If it has a larger mass for the same force, the acceleration will be less. So these are the quantities which we must know. So for a fluid, again, we must know what is the velocity. Apart from that, in order to know the force, we must know the pressure, we must know the viscous stresses. Just asking a question. Uh, have you done a studied basics of mechanics of material, mechanics of solids? Did your mechanics course have a discussion on mechanics of solids?
We have a mechanics of solids course like simultaneously going this semester.
Simultaneously. Okay, so have you already studied the state of stress?
Stress in solids, we study the beam stress and we study the basics like
Okay,
stress.
so what is state of stress? How many components of stress you have? All that you have studied.
Ah, yes, sir, that part we
Okay.
study.
No, since you're in second year, that is why I wanted to check up. Hmm. So then, what are viscous stresses? We'll discuss details of that. So the pressure and the viscous stresses, these are what will tell you how much force is acting on an element of fluid, and the density will tell you how much of mass is there in an element of fluid. So if I consider a small volume of dV of so if I have a small element dV of fluid, uh, I would be what I need to know is what is the velocity with this with which this element is moving, what are the pressure forces and what are the viscous stresses acting on this element, and what is the density of this element. So if I know the pressure and viscous stresses, from that I should be able to calculate what is the total force acting on this, and if I know the density I should know what is the total mass of this. So from that I should be able to predict um, what the so from that I should be able to derive what are the equations governing the velocity of this element of fluid. So then there are two descriptions. So if I want to measure the density or the pressure as a function of time, I could do it in two different ways. So again, taking that same example, so fluid is coming in here, going through the tank, going out. So one way would be that I keep my measuring instrument at a certain point. Say I can identify this as my point of interest, and then keep my measuring instruments here, which will tell me the velocity, the pressure, and the density at this point as a function of time. So that is known as the Eulerian description. So I know rho as a function of this, P as a function of now the concept. Now one reason why the Eulerian description has a certain shortcoming is, for a blob of fluid, we know that if we consider a certain blob of fluid and follow it as it moves, then the blob of fluid, if it is sufficiently small, can be considered to be a point mass. If it's a point mass, it is governed by Newton's laws of mechanics. So then I can apply the Newton's laws of mechanics to understand how the velocity of that blob of fluid will change with time. For that, I need to follow the material as it so I need to follow a particular fluid as it moves with time. So then in the Lagrangian description, so if I inject, my fluid is flowing in from here. So if I identify a certain small element of fluid, as it moves along with the flow, I'll take my measurements as it moves with the flow. So from the point of view of applying the conservation laws which apply to a system, so those apply to a certain mass of material. So to apply the laws of mechanics, it would seem that a Lagrangian description is preferable. But then following a particular fluid, the keeping track of it, how to do that, that is a fairly complicated, that doesn't seem to be easy. On the other hand, especially when I have if I consider this particular situation, if I have steady flow, that material is flowing in here, material is flowing out from here. In that case, if you see, the Lagrangian description will be complicated because it will come out with a velocity in a certain direction. That velocity will keep changing with time. Its position will keep changing with time. We'll have to keep track of all the possible particles which are moving in following different trajectories. On the other hand, if I'm at a fixed location, then if the rate at which fluid is flowing in here, the rate at which fluid is flowing out here are the same, then I expect the system to reach a certain steady state where, although if I follow a particle, its velocity will keep changing. If I sit in one position, I would observe the same value of velocity. So then it seems in many situations the Eulerian description might in fact be simpler. So then the question comes, can we derive the equations governing the variables in the Eulerian description? So instead of velocity of a particular particle, if I say velocity at a particular point, then what are the equations governing that? So our first task would be to derive the governing equations for velocity in the Eulerian description. Now, in the Eulerian description, since we are not following a particle, we are talking of velocity at a certain point. If we were following a particle, say when we are talking of a system of particles, we are following the trajectory of each of the particles. Conservation of mass is really not important because conservation of mass is trivially satisfied. So we don't bother about conservation of mass. We only bother about the future position and velocity of the different particles. But if I talk of a velocity field, I have velocity at various positions and at various instants of time. In that case, this description does not guarantee conservation of mass. So conservation of mass is also something we'll have to impose. Okay, so there still seems to be a serious problem because the email which was sent, I have not checked today, the email which was sent yesterday seemed to at least indicate that this week there should not be any problems about attending classes. Now, if I see, there are only 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, let me see. Okay, I think, yes, it wasn't showing all. See more. Okay, there's around 50. I hope it will pick up in due course. So from the next class, we'll actually see what are the, we'll start deriving what are the equations governing a fluid. So the serious work will have to start from tomorrow onwards. So at this point, in case you have any questions, you can ask. Okay, then we'll close today.